Hi, this is Howie Wu. I'll present S-VolSDF. It's a joint work with Alexandra Skrikos and Dimitris Samaras. We achieved state-of-the-art performance for 3D reconstruction with sparse fields by combining neural rendering and multi-field stereo prior. Nerves work very well for multi-field 3D reconstruction. Later, 4SDF gets better surface reconstruction by modeling sign distance function. 4SDF work well with dense input fields, but with sparse fields, it often tries to satisfy input images by generating some wrong surface points, with each point only visible from a particular view. It's called shape radiance ambiguity, which leads to bad results. So the solution is constrain surface points to be visible from multiple views, and this is exactly the idea of multi-view stereo. However, MVS prediction is noisy and non-reliable with sparse input fields. So the question would be how to effectively incorporate noisy MVS predictions into 4SDF optimization. And this leads to our method. Our method is a 4SDF module that can be plugged into any cost-to-find MVS model. This module adds a noise-tolerant optimization step to improve the cost MVS depth map. And this improved depth map guides the fine stage MVS. Given a reference and some source field images, we first apply MVS to obtain probability volumes. Then, to refine the reference probability volume, we multiply the probability in the reference volume with the sum of probabilities in the source volume to obtain the consistency-weighted probability volume. Essentially, it's a soft consistency check. Here comes an important observation. Given a point sampled along a viewing ray, we notice that its probability in MVS and its rendering weight W in neural rendering actually have the same meaning. The larger the value of W or P, the more likely its location should be on an object surface and also visible from multiple views. Therefore, we propose to use our consistency-weighted probability as noisy positive labels to regularize the rendering weight during 4SDF optimization. We adopt a generalized cross-entropy loss, which is crucial to increase tolerance to MVS noise. After we use the cost stage MVS predictions to regularize 4SDF training, we use the rendered depth map from 4SDF to guide the fine stage MVS. Our method performs better than both MVS and 4SDF and converges faster than 4SDF. We use the DTO dataset to compare reconstructions from 3 input fields. Our reconstruction is significantly better than both neural rendering and MVS models. We have additional results in the paper where we show our improvement remains consistent in the case of 6 and 9 input fields. In these meshes extracted from various neural rendering methods, our results appear more complete and accurate. You can plug our 4SDF optimization module into your favorite MVS model. In this point cloud visualization, the results are better for all 3 MVS models we tried. Let's look at some novel field synthesis results. Some methods also utilize an MVS prior perform worse. The reason is they try to directly learn the mapping from MVS volume to final reconstruction, which is hard with sparse fields because there are a lot of MVS noise. Here are similar results on a blended MVS dataset. Here is surface normal comparison. Our result is more accurate and complete. With our method, we achieve the best of both worlds in sparse field reconstruction by combining neural rendering and multi-field stereo. Our method is faster and more accurate. MVS fails when there is specularity. This affects our method too. We leave this for future work. Thank you for watching.